Hi, this is Peter Adamic. Welcome back. This is a spreadsheet I wanted to show you to illustrate how confidence intervals actually work. So what we're going to do here, this is on Google Sheets, we're going to draw deviates or make selections from a normal distribution with a mean of 50 and a standard deviation of 10. So we know the population that we're drawing our samples from. Now, each row in this spreadsheet will correspond to one particular sample. Now, these Google Sheets are constrained by having only 26 columns. You'll notice that the highest letter is Z. So what we'll do is we'll reserve the final 3 columns for our calculations and just use the first 23 columns for our data points. So, like I said before, the population that we're drawing from is known. It's known to be a normally distributed population with a mean of 50 and a standard deviation of 10, and you can actually see that explicitly in the first row in each of the cells. So I said earlier that each row will correspond to a sample. So let's consider the second row here. So in cell A2, we have 30.4 and a bunch of other decimal places. And that's a random draw, a random number generated from the normal distribution that has a mean of 50 and a standard deviation of 10. And this will be the same formula for every single cell. You'll notice that the syntax in the cell is equals NORMINV. So it's a normal random variable. It's random, so you put RAND, open bracket, close bracket, and then you specify the mean and the standard deviation of that normal random variable. So that's the syntax in Google Sheets. Okay, and then we can copy that across rows and down columns to generate a large number of simulated values. We call them deviates in statistics, drawn from that distribution. And the distribution is not changing here. So we can treat, for example, the second row as one sample drawn from this population. Now the sample size will be 23 because there's 23 columns. And then for the second row, there's going to be 23 numbers. Okay, so we have 23 numbers generated randomly from a known distribution, normal, mean 50, standard deviation 10. Now we can calculate the confidence interval based on our sample. So we're just in row 2 now. Again, pretend that's our sample that we have. Using our formula that we've derived, we have X bar, the sample means, that would be the average from A2 to W2, and then minus 1.96, that would be the 97.5th percentile, of the standard normal. So if we're constructing a 95% confidence interval, we're going to want to use 1.96. And then we multiply by 10, which is the standard deviation, and divide by the square root of n, which in this case is 23. Now, column Y will have pretty much the exact same formula, but we're going to add instead of subtract. So this will be the lower end of the 95% confidence interval, in the X column, and in the Y column, we'll have the upper end of the 95% confidence interval. The last column, Z, is an indicator of whether it's an indicator, 1 or 0, of whether 50 is contained in the interval or is not. So we're going to give, there's just a logical argument in the cell. If x2 is less than 50 and if y2 is greater than 50, we'll assign a 1, otherwise 0. Okay, in other words, if 50 is in the interval, we'll give it a 1. If it's not, we'll give it a 0. Okay. We can do this a large number of times, and in fact, that's what I did in this case. I think it was 2,000 times. Yeah, so we'll go down to row 2001 because, of course, the first row was not a sample, right? It was just the R norm 50, 10. I didn't necessarily have to put that in the first row, but I did to be explicit and to help us have the right bearings. And what do we notice? So if we go across to the bottom of row Z, we have another final calculation. It's the average of all of the numbers, all of the zeros and ones that are contained in row Z. In other words, what proportion of the time will the confidence interval that we calculate for each sample, what proportion of the time will it contain the true mu? And we know the true mu here in this case because we know that we're drawing from an artificially created population that has a known mean of 50 and a known standard deviation of 10. And it's also known to be normally distributed. So we know the exact attributes of the population that we're drawing from when we construct these confidence intervals. And what you'll notice is that we get in this simulation around 95%, 95.55%, excuse me. Now, if we want to do another simulation, I could just hit the space bar and then do another simulation, we get 94.75% or 0.9475. We can do it again. In this case, we get 94.05. Again. So we get 94.2. We do it again. We get 94.95, so closer to 0.95. I guess I want to see one over 0.95. I just want to, yeah, here we go, 95.4. So it's going to hover around 95%. Okay, so this is the way you should understand what a confidence interval is. A confidence interval is one of these that you're going to calculate for one specific sample. Okay, so in the long run, as we construct these confidence intervals, 95% of the time, they will contain the true mu, which is 50, and 5% of the time it won't. Okay. Hopefully that made or helped demystify what confidence intervals are actually doing. Now, you still might be wondering, well, is there not then a 95% chance? Is there not a 95% chance that mu lies in any specific interval? Well, we talked about this earlier. It's either 0 or 1. Like, I've highlighted this one arbitrarily. 1, 2, 3, 4, the fifth one. So 45.9 to 54.08. Now 50 is in that interval, right? But it's either 0 or 1. Either 50 is in the calculated interval or it is not. So objectively speaking, it's certain that 50 is going to be contained in the interval. However, we don't know that in most applications. We don't know the population distribution in most applications like we do in this simulation. So in real life, if you were to construct a confidence interval, you would not know whether the answer is 0 or 1. So if you're constructing a 95% confidence interval in real life, under the assumption that we're sampling from a normal population, which is an assumption in real life, right? We don't actually know that here. But if that and some other assumptions are met, then your best subjective guess based on the calculated interval that you have, you could assign a probability to it, but there's caveats built into that. It's better, and that's only if you have to append a probability to the calculated interval. If you do not have to do that, then the best interpretation to give your confidence interval is the long run frequency interpretation that, say it's a 95% confidence interval, then 95% of the time, the confidence interval that you calculate will contain the interval, and 5% of the time it won't. Okay, I hope that helps. Like I said, I use the word demystify, but helps demystify what it is confidence intervals are actually furnishing or providing when you calculate them. Okay. All right, great. Thank you very much, and talk to you next time. Bye.